All right, so we're going to fast forward up into the section 2.7, which is called rational functions, and that starts on page 269. So the first thing we have to figure out or make sure we understand, and we have talked about this a little bit before. We did some stuff with this in our prerequisite chapter back in first quarter. What is a rational function? Well, a rational function is a new function f. We're calling it f here. Oops. A new function f here. And it's comprised, it's in a fraction form. If you remember, rational numbers are numbers that can be written as fractions. So we have a numerator and denominator, and then the numerator, we're going to have a whole nother function. So it could be a polynomial up here. And in the denominator, we're going to have a different function. So it's just a fraction made up of, the two parts, the numerator being a separate function than the denominator. So the first thing we're going to talk about with these rational functions are domain, and hopefully you remember a little bit about domain from before, but when we do a couple examples that should refresh your memory, and also asymptotes. And I assume that you've heard the word asymptote before, and usually it's defined, at least at this level, as a line that the graph of the function approaches. And so that's a pretty decent way to look at it. We get a little fancy up here with some of the notation, and I'm going to explain that as we go. But if you can keep in mind that an asymptote is a line, horizontal or vertical, that the function approaches as the function goes to infinity, or toward that number. And so I'll try to keep that straight for you. So they start here with a pretty simple function of 1 over x. And they're pointing out that they're saying, hey, look, there's a horizontal line here that if we extended this out like forever, this function would never really get to this x-axis in either direction. And they say, look, well, there's a vertical line. That was the first one's a horizontal. Then there's a vertical line here that kind of plays in the same nature. So as we get closer, as this function gets closer to this y-axis, the function keeps getting closer and closer and closer to it. And that comes in both directions. And so the both directions thing is what they're talking about up here. Okay, and this is a little bit of, it's pretty simple to understand, but it's kind of an advanced notation kind of situation. And so they're saying, okay, well, let's look at our function. And we're going to look at it as x approaches 0 from the left. Okay, so that means that we're coming down the x-axis from the left, getting closer and closer to where x is 0 right here. And as we do that, notice that the y values shoot off way down into negative infinity. So as we approach 0 from the left, that's what that little negative sign is saying, from the left, notice that the y values approach negative infinity. But if we go to that same x value 0 from the right, and that's what that little plus sign is saying, then our y values, our f of x, go up to positive infinity. And they're saying, well, that's a vertical asymptote. Okay, so then the way this part is read, and this is referring to the horizontal asymptote here, as x goes to negative infinity, so we're sitting here and we're going out to negative infinity, notice that the y value creeps up and up and up and gets closer to 0. And then when we go to the other side, when we go x goes to positive infinity, right, this function gets closer and closer to it gets closer and closer to 0. Okay, we're going to say that's a horizontal asymptote. Okay, and so then they give you the definition of a vertical and horizontal asymptote. So it is a line, right? It is a line right here. The line x equals a, so that's going to be a vertical line, is a vertical asymptote of the graph of f if the y values go to infinity or negative infinity as x gets closer and closer to that number a. A in this case is just some number, either from the right or the left. So you won't have to worry too much about coming from the right or the left. Like I said a little bit ago, that's a little bit of an advanced idea, but just understand that it is a vertical line, and you can write it as x equals some number. And as we get closer, as our x values get closer and closer, right, that arrow means as they approaches this number, then our y values are either going to positive infinity, right? Y values approach positive infinity, or maybe they approach, they being the y values, approach negative infinity. Okay, and then they're saying, okay, well, what's a horizontal asymptote? Well, there's another line. This line is going to be horizontal, y equals some number b. And it's kind of like the backwards, backwards thinking of the vertical. As x goes further and further down to the right, go down to positive infinity, then our y values get closer and closer to whatever number we're talking about. Okay, so they're both lines, or as x goes to negative infinity, way out to the left, right, our y values approach that same number, and those would be horizontal asymptotes. So a little bit of definitions. Shouldn't be, like I said, I think you should have heard of asymptotes before. And now down here at the bottom, right, they give you a couple more examples. Okay, different graphs of producing different asymptotes. So let's look at a problem. Let's look at a couple problems that we can talk about. Well, no, we got to do let's do the next page here. So go to 271. Right, because we're going to talk a little bit more about horizontal asymptote. Now, this thing looks awful to look at. Now, we've actually talked about like trying to read math a little bit, and I know that's very intimidating. But all they're saying is that our numerator function, let's put that in descending order, right, where the first term has the biggest degree. And let's put our denominator function in descending order again, where our first term has the biggest degree. And so that's all they're saying with this. Like, make sure that you have arranged it, at least in your head, from the biggest exponent to the smallest exponent. And as long as you do that, and you assume there are no common factors, so like if you factored something it could cancel, then all we're doing is comparing these two degrees. Okay, and that's this horizontal part. I guess I'm doing the horizontal part first, and I'll come back and do the vertical. Okay, so we've arranged them in descending order. Let's compare the degrees and see what happens. Okay, and it says if n is less than m, then we has a horizontal asymptote here. So what they're saying is, if the degree in the numerator is less than the degree in the denominator, okay, so like the degree in the denominator is the biggest, right? This is the biggest function. Then we're going to have a horizontal asymptote at y equals 0, which is the x-axis. Okay, that's all it's saying. So again, if the degree in the denominator is bigger than the degree in the numerator, you have a horizontal asymptote always at y equals 0. Okay? If the degrees are the same, again, we've arranged these in descending order, and now we're looking at the degrees. If they are the same, if they're equal, then there's a horizontal asymptote at this weird place, okay? But this weird place is just the coefficients, the leading coefficients. So again, if the degrees are the same, you just take the leading coefficients of the numerator and the leading coefficient of the denominator and put them over each other, and that's where the horizontal asymptote is. Okay, and then we'll go over an example. And then finally, if the degree in the numerator is bigger than the degree in the denominator, then there is no horizontal asymptote. Okay, so then they talk about vertical asymptotes here. So I skipped that part originally. And so the graph of f has vertical asymptotes at zeros of q of x. So basically what they're saying is that take your denominator, set it equal to 0, and solve. And for every x value you find, that would be a vertical asymptote after you've canceled, after you've factored and canceled. Okay, so this won't come into play too often, but it could. Okay, that doesn't give you an asymptote We can talk about that later. Okay, so that's going to be the procedure, right? To find your vertical asymptotes, take your denominator, set it equal to 0, and solve. To find horizontal asymptotes, all you're doing is comparing the degree of the numerator and denominator. So now let's do a problem. All right, so for this first section, they say find the domain of the function and identify any horizontal or vertical asymptotes. Okay, this is on page 278. This is number 2 here. So let's start with the domain. You remember domain is all the x values that your function is allowed to accept. Okay, and so usually you always start off with the idea that all real numbers will work, but you're looking for specific situations. And for rational functions, we're worried about zeros in our denominator. Okay, this is already factored out. It's a cubic factored out. And so then what you would do is set that denominator equal to 0. And if you remember correctly, if you have a bunch of factored things set equal to 0, you can just set them equal to 0. And I'm not going to do it 3 times because we're going to get the same answer. But x being 2 would be a problem, because what we're saying here is if we had 2 as our x value and plugged it in, we'd have a 0 in the denominator, which is bad news. So then our domain is going to be all reals, except that x is not allowed to be 2. And now they want to identify any horizontal or vertical asymptotes. Okay, so it's probably a good idea to get in a habit of checking to see if you can simplify these rational functions at all. And this one you cannot. And so as long as you cannot factor or can't, cancel any factors, then your vertical asymptotes will be the same as the excluded values. Okay, and that term is going to come up in the IXL. This is an excluded value. So our vertical asymptotes are going to be the same as the excluded value. So then vertical asymptote would be the vertical line x equals 2. And now we're just checking, we're going to do the horizontal asymptotes. Okay, and all we're doing with that is comparing the degree of the numerator, which is 0, to the degree of the denominator, which would be 3 if we expanded this all out. And saying, okay, well, so since our denominator has a bigger degree than our numerator, that means that we have a horizontal asymptote at 0. Okay, so we'll run through 4 and 6 because they give you all the options for horizontal asymptote. But again, the domain, we're going to start with the domain, and we're going to set the denominator equal to 0 and solve. And so then our domain is all real numbers, but x is not allowed to be negative 1/2. That's our excluded value. Notice there's no way we can factor either the numerator or denominator any further, and so they will not cancel out. So that's telling us that our vertical asymptote is the same as the excluded value. So it's the vertical line x equals negative 1/2. For our horizontal asymptote, we are comparing the degrees. Pay attention, in the order. This is our leading coefficient and our leading terms. Okay, so again, that statement on page 271 is saying if the degree of the numerator and the degree of the denominator are the same, we will have a horizontal asymptote at the leading coefficients, like the leading coefficient of the numerator over the leading coefficient of the denominator. And it's really easy, you can just graph that and check to see that it's accurate. All right, so again, number 6, the domain we'll start off with. You should always start off with that. You take the denominator, set it equal to 0, and solve. So it's all reals except for -1. That's the excluded value. Again, you should check to see if you can factor and cancel anything. And again, we cannot. So that implies that our vertical asymptote is the same as the excluded value. It's the vertical line at -1. And now for the horizontal asymptote, we're just comparing the degrees of the numerator, 2, to the degree of the denominator, 1. Since the numerator is bigger, since the degree of the numerator is bigger than the degree of the denominator, there are no horizontal asymptotes. Okay, so I'm going to jump up ahead to number 14 here. 7 to 12, you could totally just put them in the graphing calculator and match them up. But the idea is that you look at our vertical asymptote rules and our horizontal asymptote rules and see if you can match them up before. Okay, and that's where we want to be, is that you can look at things and kind of identify what's going on without having to use the graphing calculator every single time. But 14, I think, is an important one, because when we were doing those first examples, those first 3 examples, I talked about starting with the domain and then moving on and checking the vertical asymptote. And a couple times I mentioned, you should factor and see if anything cancels, because even in our definition they talked about that something important happening there. And so 14 is kind of talking about that. And so they give you, they say determine the domains of f and g. And so here's f, and then g would be just x here. Oops. Yeah, but let's try that again. So g would be just x. Okay, and they're saying determine the domains of f and g. Okay, so let's just do that first. So the domain of g should be nice and easy, right? That's going to be all real numbers. But let's look at the domain of f. So again, we take our denominator, set it equal to 0. And how do we solve that? Well, hopefully you realize that you have to factor. So we're going to take an x out and be left with x minus 3 equals 0. And so now we set each of those equal to 0. So, and then solve. Okay, so the domain of g was all real numbers. But you see these down here, these are problems for our domain of f. So for f, the domain is all real numbers, but x cannot be 0 or 3. So we did part B, so different domains. And they say find any vertical asymptotes of f. Okay, so let me rewrite f in its factored form so we can take a look at that. Okay, and so then what you should see there is that we can actually cancel some of these factors. The x minus 3's cancel, and one of the x's actually cancels also. So it turns out that after canceling everything, we actually have the same function. And that means, actually, since we could cancel them, that there are no vertical asymptotes. Excuse me, no vertical asymptotes. Okay, so if you graph both of these on the, if you put this in exactly into y1 and you put this in just like this into y2, it's going to graph what looks like the same line. But we know that we cannot have 0 or 3 in this one. So if you were able to zoom in on that graph, if you were able to zoom in on that graph, right? Y equals x is just this line here, okay? You would see that the graph of f would have a hole right there at 0 and right at 3. Okay, so then the general rule of thumb goes like this. If, you know, your domain is your domain. Your domain is your domain. Okay, so no matter what, you always got to check your domain with the function as is. But then you should always try to see if there's anything you can cancel. So if there are things left in the denominator, then whatever is left is a vertical asymptote. However, if things get canceled like they do here, you know, we don't have anything left in the denominator, right? We just have x. And so then these are just holes in the graph. Okay, they're just simply not there because they're not allowed to be there because of the original. Okay, so I'm going to let you think through 15 and 17. We can talk about that at some point, but that's a good thought thing. In fact, it says think about it. But I do want to do number 20 to talk about what's going on here. And this is going to be an important problem for you because, by the way, it's going to be on the quiz. Or something very similar, at least, will be on the quiz. So make sure you understand what's going on here. And they use a lot of words that maybe you don't really feel comfortable with. But it says part A here, determine the value the function f approaches as the magnitude of x increases. Okay, so what we're saying is as x gets really big, and when we're talking about really big, we're not talking like 100,000 or even a million. We're talking like 100 billion or whatever, right? Like this is growing huge, huge, huge. So really what they're asking here is about your horizontal asymptote rules. So this part of this fraction is fixed. It's just at 1. So if you think about the degree of the numerator here, it is 0, and the degree of the denominator is 1. So as x gets super, super big, as x is approaching infinity, what is this term doing? Well, our horizontal asymptote rules say since the degree in the denominator is bigger, that this term is going to 0. Okay, and another way to think about that is if you divide 1 by, and you can check this out, like if you divide 1 by 1,000, and then you divide 1 by 100,000, and you divide 1 by 100 million, you'll keep getting closer and closer to 0. So part A, as x gets crazy big, that's what it's saying, then so as x gets super big, our function gets closer and closer to 2. Now, that's going to be true whether or not we're going to positive infinity or if we were going to negative infinity. Because we are really getting such a big number that basically either direction, it's going to 0. So now part B is saying, or B and C, is f greater than, so is this, well, let me just read it first. Is f greater than or less than this functional value, and this functional value in this case is 2? Is f of x greater than or less than this functional value when x is positive and large? So let's look at that first. That's part B. Okay, so again, oops, hold on. So what's going on is x is going to only positive infinity here. Okay, so what they're saying is as x is going to positive infinity, are we bigger than 2 or are we less than 2? We know eventually we'll get to 2 because that's what we're saying here, because if this is going to 0, then this value is going to 2. But it actually matters if we're going to positive or infinity or negative infinity. Because if we're going to positive infinity here, this value is always just a little bit bigger than 0. So it's always going to be positive. So then our functional value will actually be a little bit bigger than 2 the whole time. So the question is f of x greater than or less than this functional value? So when x is going to positive, y is actually greater than 2 the whole time. And again, the reason that's true is because we're always adding a positive number, super, super small, but just a little bit bigger than 2. Okay, and so then, like now they're asking, so for part C, it's saying, the same question. Is f greater than or less than this functional value 2 when x is negative in margin magnitude? So again, what they're really asking is, what's going on when x is approaching negative infinity? Well, if x is approaching negative infinity, we keep plugging bigger and bigger negative numbers in. So then actually, as we get to negative infinity, we're still getting to 2. But really, we're always going to be just a little bit less than 2 because we're always subtracting just this really super small number. So then we're always going to be less than 2. And that's going to be true the whole way as we keep getting closer and closer to 2, will always be less than 2. So hopefully that makes sense, and you should be able to get 1 of 21 down, and make sure you ask questions in the next time I see you guys.